Can you hear me? Okay, good morning everyone. Welcome to another webcast brought to you by the guys here at Innova Systems. My name is Matthew and I'm going to be doing an introduction to SolidWorks Simulation for you. So without further ado, let's jump straight in. First of all, I'm just going to go through a bit of a background of FVA analysis just to bring you guys up to speed with what's going on behind the scenes before we go and run some analyses ourselves. So first, what we're going to look at is what static linear finite element analysis means to us. Well, finite element analysis is a numerical method for approximating the displacements and resulting stresses in our components as a result of loads that we're applying. What SolidWorks is going to do is break up our model into a number of finite elements, hence the name, and then we're going to use each of those elements to calculate approximations for our displacements and resulting stresses. As a sort of visual gauge for this, if you can just have a look at the curve that we've got on your screen there, that's quite a complex curve, and if, say, this was representing the surface of one of our models, it's quite a complex curve to try and generate simulation results for. So what instead we're going to do, using our finite element process, is we're going to break it down using a number of points, and then we're going to approximate that curve by bridging each of those points with a straight line, and that greatly simplifies our solution process. Now, what does that mean to us in terms of SolidWorks? In SolidWorks, hopefully you're all aware that we've got a simulation tool which allows us to do this FEA analysis. SolidWorks Simulation uses this finite element method. There are other methods, the boundary element method, finite difference method, finite volume methods, which have all been used across the years, but FEA has really grown to dominate the market, and now all of the other systems have become a little bit more niche, and so they're used for very, very specialist situations. So in SolidWorks, using the FEA finite element analysis tool, we can quickly swap between our design interface, which you'll all be familiar with, and our simulation analysis tool. This allows us to use the simulation tools not only to analyze whether our design is sufficient, but also we can use it to drive our design because we can switch back and forth so easily. Now, when we say static analysis, we are making a couple of assumptions. So the first being the static assumption. We're going to take the equation of motion that we would usually use to model the reaction of, say, a model to an impacting force. And just breaking this down for you, the first term here, the signified by the M, represents the inertia matrix of our geometry, and that's related to the acceleration of our design, of our components or perhaps nodes of elements, which we will come back to later. The C represents our damping matrix, so this is the damping properties of the material in the model. That's related to the velocity of the geometry, and that's the first derivative of the displacement, obviously. And then the final value we've got there is the stiffness matrix, represented by the K. When we say we've got a static analysis, what we're doing is we're assuming, first of all, that the loads are applied slowly, so that we're not seeing any dynamic effects. We're not seeing a vibration or anything like that as a result of a sharp application of force. We're also assuming that the loads are constant, so that force term that we see on the right-hand side there isn't varying with time. And this allows us to greatly simplify the equation by removing all of the time-dependent values and leaving us just with the force on the right-hand side of our term and the stiffness matrix and the displacements on the left-hand side. So what SolidWorks is going to do is just determine the stiffness matrix of our geometry, apply the inverse of that stiffness matrix to our force, and that's going to output our displacements, and then we can go from there to determine the stresses, etc. Now, one thing we do have to do when we're about to conduct a static analysis is just have a quick sanity check to make sure that we are going to be modeling sufficiently the situation. because when we say static, we are ignoring some of the dynamic terms. Now, in some situations, that's absolutely fine. If we are placing a load upon a table, that's fine. We're not expecting any dynamic loads. But if, for instance, we look at our model and we are expecting dynamic loads, we need to assess whether the static assumption is still okay. So first of all, we're going to see whether our system is dynamic, and then we need to see whether those loads are important. And this can be really key because in a dynamic model, the loads that we generate can be up to 1 over 2 times the critical damping factor, which is signified by zeta here, times the static load. So say, for instance, if we've got a dynamic situation where the damping ratio is 5%, that can lead to dynamic loads of up to 10 times the static loads. So we need to make sure that we're doing something sensible there. We can come back to dynamic loads later on, and there will be further webinars related to dynamic analysis further down the line. The next assumption we have to make is the linear assumption. Now, this is assuming full compliance with Hooke's law. Hopefully many of you will be familiar with this relation. This is direct proportionality between the stresses and the strains within our model. Essentially, we're assuming that the force is directly proportional and hence linear with any of the loads that we are applying. Here we can see the graph that we've got on the screen there signifies this, so we can see with the linear analysis the displacement is increasing with a linear relationship to the force. If we were to consider nonlinear effects, which can be incurred when we're looking at exceeding the yield strength of a material, or perhaps if we're seeing large deflections, we may see some stress stiffening or softening, which would vary that result. That's where this assumption comes in. If you have a look at the graph, you should hopefully see my mouse hovering around the linear portion of that nonlinear graph, and that's the region that we're working in here when we're looking at a linear analysis. So just to reiterate, the linear analysis assumes that we're not reaching the yield point of any of the materials here, and we're also assuming that the deflections are small, such that the stress stiffening and stress softening doesn't occur. Okay, now hopefully many of you will be familiar with the term meshing. It's also referred to as discretization, and that's just the process of breaking our model. So say, for instance, here we've got a hex nut with a flange on the bottom. That's the process of breaking that solid model down into a number of finite elements for our analysis. So what we're going to do is instead represent this geometry with a number of tetrahedral volume mesh elements. You should hopefully be able to see a sort of depiction of that on the bottom there. Hopefully, if you can get your head around it, you should be able to see we've got 4 main nodes dictating the 4 vertices of that solid mesh element. And what SolidWorks is going to do is it's going to break our model down into a number of these elements, and later on the solver will be calculating the displacement and stress results at each of these nodes. So here on the right hand side you should see a pictographic representation of our meshed solid geometry. And like I said, what SolidWorks is going to do is determine the stress/strain results at each of the nodes on these elements. If you can imagine, each of these nodes can move in the x direction, y direction and z direction, giving it 3 translational degrees of freedom. If we are going to determine the results for each of those 3 degrees of freedom at each node, hopefully you'll appreciate that with 4 main nodes on an element, each having 3 degrees of freedom, that's 12 degrees of freedom, which each serves almost as an unknown in a set of simultaneous equations. So for instance here we'd have 12 simultaneous equations to determine the stresses and strains in this element. As we try and break down the rest of the model into these elements, you can see how the number of unknowns in the equations increases. So finally SolidWorks is just going to determine the displacements of those nodes, so hopefully you'll see this deformed mesh element, and once we've determined that deformed result, we've solved each of those simultaneous equations, we can start looking at the stresses and the strains. Now, when we break down our model into a number of mesh elements, we can't help but incur some errors. Now, as engineers, we're all familiar with the way in which we have to make assumptions. We have to model certain elements of our studies or certain elements of our calculations, because it's not always feasible or practical to try and solve an exact solution, so we use models instead. The first of our errors that we can incur when we're using this model is what we refer to as an idealization error. And this is associated with the user input. So this isn't an FEA analysis error. This is generally associated with sloppy geometry or say models that don't represent the actual physical situation prior to using the FEA tool. And that's not so important when we're looking at the FEA side of things. That's something that you need to sort out before you bring it into the FEA tool. The next error that we can incur is the discretization error, or the meshing error, which is an inaccuracy introduced by the geometric assumptions. So when we are breaking down our model into those mesh elements, we can incur some inaccuracies where we're not fully resolving, for instance, curvature or smaller features because our mesh sizes might be too big. Now that's the one that we do have the most control over, and we will see some of that control later on when we go to set up our analysis ourselves. The final error that we can incur when we're using the FEA is the solution error. And this is something that we don't really have control over. These are just rounding errors accumulated by the mathematical solver itself. Thankfully, these are very, very small, and the mathematics which deals with these errors is being improved all the time. Okay, so now we're just going to have a quick look at the workflow that we're going to use to set up our study. So there's a number of steps which are very, very simple, very straightforward that we go through. The first is starting with our geometry. So here you'll see we've got a spanner, which is what we're going to have a look at later on. And this is our actual model as designed, as we would like it to be produced from SolidWorks. So you'll see here we've got a lot of details, we've got some text, we've got a lot of aesthetic rounds on the outer edges there, which when we look at it, if I was designing this spanner, these things aren't offering any real structural significance. So we can take these out. And that's what we do next. We go through a process of defeaturing, cleanup, and idealization. Now these are the three key processes to setting up our study. Defeaturing refers to just suppressing or removing insignificant features. So for instance, the text that we see here where it says lightweight spanner, we don't really need that. It's not offering any support, any weakness, so we would take it out. Idealization refers to a much more aggressive form of defeaturing. So this is when we may start to depart from our actual CAD geometry. Perhaps we might be modeling very, very thin features, for instance, sheet metal with a surface instead of an actual solid mesh on a very thin part. And that's it's a more aggressive method that can introduce more error, but sometimes it's necessary, and you'll see that later on in further webinars. And then finally, the cleanup is fixing geometry that perhaps the CAD side of things can tolerate, but the simulation won't. For instance, if we're looking at modeling a press fit, we might model two parts to intersect with one another in the CAD side of things, because that's how we would want them to be produced. Whereas in simulation, we can't have two models intersecting because the mesh elements will intersect with each other, and that causes the maths to fall over essentially. So there's a certain element of cleanup we have to do in order to enable us to run the study. So then we come through to our next step when we've got our simplified model, which is much, much cleaner, much simpler to model, and it will hopefully, because we've been through these steps, it will mesh a lot quicker and we'll be able to solve a lot quicker. The next step is setting up our mathematical model. So this is just applying our loads, our restraints. We tell SolidWorks what materials we want to use, which brings through all of the material data, so its strength, its mass, its density, etc. And we obviously need to tell SolidWorks what type of analysis we want to conduct. In this instance, we're going to use the static simulation, which is available in SolidWorks Premium. There are other types of analysis we may wish to specify if we have further simulation tools such as thermal analysis, buckling analysis, etc. And then the final stage before we solve our model is to break it down into this mesh, so discretizing our model so that SolidWorks can calculate the results at each of those nodes, like we said before. And then obviously the final stage is just to run it and achieve our FEA results. There's a lot of tools that are available in SolidWorks that allow us to analyze the results in great depth, and we can get a lot of really handy information out of there, which is really, really useful, because if we were, say, conducting a physical test, you don't really get too much information. Maybe you'll see a failure, you'll see something that's broken, and you can see where it's broken. Whereas with the simulation tools that we've got available here, we can see why it's broken. We can see how stresses were propagating throughout the model. We can see where stresses may also be reaching high values, but we didn't see a failure in the physical test. That's what's really, really handy here. Okay, so what we're going to do is have a look at this spanner. First of all, I'm just going to set up some of the forces that we're going to apply. So here you'll see a table of data. This is taken from, you'll see the website on the bottom there, from nylonalloys.co.uk. And this is a set of data for nylon bolts and screws. So what we're going to do here is we're going to try and optimize our spanner design so that we can make it as lightweight and we can use the minimum amount of material volume as possible, but maintain sufficient structure in order to allow us to tighten up a nylon bolt to the specified level of torque. So we're going to be making our spanner out of nylon also, and you'll see those material properties when we go through to the actual model. So in this instance, we've got a 10mm spanner, so we're going to be using an N6 bolt there. So you'll see there, we don't really want the bolt to be reaching a deformation value, so the peak torque value we could apply before seeing any deformation within the bolt is 1.47 Newton meters there. So we're going to bring that value through and make sure we keep hold of that for later on. Next, we're going to have a look at our spanner. You'll see I've got two labels there. The first on the left-hand side, we can see the location of the center of that nut, which we will see later on in the model. And we've also got the location at the center of where we're going to apply that force. You can see we've got a couple of split faces here, so we've got one region here where we're going to be applying the force. Just as an approximation, I've taken the torque value to be applied at the center point of that force location. So if I just measure up these lengths, we can see that the perpendicular distance, or the moment arm, for this situation is 0.0879 meters. So all I need to do is bring that through, divide the torque that we're looking for by that distance, and we can see we need to apply 16.72 newtons. So now let's switch over to our model and have a look at running our simulation. So what you first of all hopefully see on your screens now is the spanner model that we've been talking about, and we've got a couple of variable configurations here. Like I said before, one of the things we don't need is aesthetic detail. So for instance, the text that we've got here, the small rounds that we've got around the outside of this, the open head, we've got a couple of rounds on the closed head as well that we don't really need. So we're going to switch over to the simplified configuration, and you'll see that that's much simpler. We've also got a couple of other variations of design which we're going to test, and this is part of our optimization process now. So we're going to go through running some simulations on a couple of different designs and see which one's best. So if I can direct you to look at this region here that's highlighted now on your screen, if I select the 2mm bar fill version, you'll see that that fill area in the middle there reduces slightly, so we've got slightly less material in the middle there. If we have a look at the 1mm fill, as you'll expect, it gets a little bit thinner again. We've also got another 2mm fill with a shell on the open head here. So we're going to go through and run a simulation on each of these designs and just see which one's going to be the best for us. So first of all, I'm going to have a look. If I switch back to our simplified model, I'm going to have a look at where we're going to apply that force. Before we go into SolidWorks simulation, we need to give some thought about how we're going to set up our study and whether we need to make any changes to our geometry in order to facilitate any new features that we might need, for instance, force application areas. So what you'll hopefully see here on the left-hand side is that I've produced a sketch already, which is just two straight lines that I'm going to use to split these faces here, so that I can apply a force just to those regions only. which is simulating the presence of a hand at the end of the spanner. You wouldn't be applying the force along the full length of the spanner. It would be concentrated along one region, which is what we're going to try and simulate here. So if I just select that split face sketch there, I'm going to come in, insert a split line. Because I had that sketch already selected, it's going to pull through. And now I'm just going to select these three faces and hit OK, and you'll see that now we've got that split face. So now we can specify a force on only these regions instead of along the full length. Now that hasn't changed our geometry at all. We haven't cut the spanner in half or anything like that. We've simply applied a tool which allows us to select one specific region of the face instead of the whole face. Now, one thing you'll notice, if I switch through to the other configurations, that split line hasn't pulled through. Now, one thing that you really need to get used to when using simulation is the use of different configurations and how you can set them up with varying designs so that you can quickly assess different models. So if I right-click on our split line here and ask SolidWorks to configure the feature, you'll see that we've got a list of all of the configurations here, and a number of them have that feature suppressed. If I unsuppress that feature in each of these, you'll see that when I switched over to each of the configurations now, that split line has pulled through, and so we can use that region to apply the force for each of those individual models. Okay, the next step we're going to do is make an assembly from our part, because we're going to, we'll have a look at the material first before I do that. So if I just edit this material, you'll see that I have generated my own custom material because it was a material that wasn't in the SolidWorks database. It's very, very simple. We can just right-click and ask SolidWorks to generate a new material. Here we've got a nylon type 612, which is typically used for molding, and I can come in and input my own values here from any external resource. For instance, a very handy website is matweb.com. Which has a whole list of material properties that we can stick in there for us. Okay. Also note a tool that I've used here. If I come in and add sensors here, I can use sensors to monitor the mass and the volume of our design and how it varies between different configurations, which is what I've used as part of our results convergence tool. So later on when we see the results, you'll see that I'm comparing them with the mass and the volume used. Okay, now we're going to go through and have a look at a assembly of our part. So we're just going to hit OK, which is going to include our spanner. I'm just going to hide that sketch so it doesn't get in our way. And I'm going to use a toolbox component. All I'm going to do is come over here, expand the ANSI metric list there, and go to the hex nuts. And I'm going to drag in a hex nut with a flange. I'm going to tell SolidWorks that I want that to be an M6. I'm just going to hit OK. Now the next thing we need to do, because it's still floating around, is apply our mates. Now this we can do very, very quickly. I can specify a couple of mates just to move our nut in place. The last one I'm going to do is grab that edge and make him coincident with that edge just there. And now you'll see that our model is fully defined. So that is the assembly setup using our simplified configuration. But obviously we've got a couple of other configurations of our spanner that we want to assess also. So we're going to generate some other configurations of the assembly too. If I right click on the spanner just here in the feature manager, the feature tree, we can come through and configure that component also. And we can use this menu to generate new configurations too. So for instance here, I'm going to put the 2mm fill configuration in. I'm going to put the 1mm fill configuration in. And I'm going to put the 2mm fill and shell configuration in, just like so. I'm also going to come back and edit the default name for that first configuration later on so that it reflects the simplified, just for a bit of clarity. Now all I need to do is, using the configuration list here, is come through and select the appropriate configuration reflecting that assembly, like so. And now we'll see after I just rename this to simplified. And now we'll see that we've got a configuration reflecting each of those spanner configurations. Now the final thing we need to do is actually set up our static study. So making sure that I've got the simplified configuration active first, because that's the first one I'm going to study. I don't want the advisor. I'm going to generate a new study, and we're going to call this study, for a bit of continuity, I'm going to call this simplified, and hit OK. So that brings us straight through to the simulation interface, and you'll see how quick and easy that is to do. So that's going straight from the assembly mode into the simulation mode with very ease, or with a lot of ease, sorry, and not a lot of time incurred. So what we've got here on the left hand side now in this tree is, first of all, a list of the parts that we've got included. So we've got the spanner and the hex flange nut, and you'll see that on the right hand side of the name of the spanner we can see what material has been applied to it. We haven't got a material applied to the hex nut, and what I'm actually going to do is ask SolidWorks to ignore the material and just make that rigid for the time being, because we're not concerned with any of the stresses inside that nut. We're just concentrating on the spanner itself. Next, we've got a global contact, and this is set to bonded for the time being, and that's okay, because what SolidWorks is going to do using that bonded contact is it's going to assume that anything that is already in contact within our assembly, for instance the inside faces of the spanner and the head of the nut, because they're already in contact, SolidWorks is going to assume that they are bonded as specified in the global contact just there. The next thing we're going to do is apply a fixture. So we've got a fixed geometry on the inside of that nut, and then we're going to apply an external load just by right-clicking on the force on the left-hand side, which brings up the force tool, and we can specify that force on each of these faces that we created earlier. Now notice at the moment that the force is coming in signified by these arrows normal to that face at every instance. What we can instead do is use the select direction tool and just grab a face which is normal to the direction that we're after, specify that we're going to use a total force, and in here if we add the 16.72 newtons that we calculated earlier, you'll see that SolidWorks has now changed the direction so that in total we are applying the 16.72 newtons all in one direction spread across those three faces, which is exactly what we're after. The final thing we need to do before we can run our analysis is set up our mesh. So you'll see already that we're pretty much there, which is very quick and easy. The mesh tool is as easy as everything else that we've seen so far. Now we've got a couple of details within our model that we're going to try and make sure that we resolve more accurately. So we've got the opportunity to use mesh controls here. So right-clicking on the mesh tool again on the left-hand side, we bring up this mesh control tool. If I right-click on one of these internal faces here and ask SolidWorks to select the tangency, I can grab all of those tiny faces in there. I can do the same on the bottom side. And then I'm just going to come through and specify a mesh size of 0.2 millimeters on here. Now, I have previously run this study, so I do know what typical values to put in, but you'll see it's a very visual process which gives you a lot of feedback, and you can go back through and make changes to your mesh with relative ease. So the next thing I'm going to do is apply another mesh control on the outer edges of the spanner. Now these are typical areas where we're expecting to see stress concentrations. That's just based on my common sense, which is a feature of every engineer, I guess. I know where I'm expecting the stress peaks to be, so I'm just going to try and resolve the geometry in those areas slightly more accurately, just to improve the accuracy of the result. So if I stick 0.4 millimeters in there, that's the setting that I'm after. And then the final step is to right-click on the mesh, go to Create Mesh, and we've got a set of parameters that we can specify here. I'm going to use a 1 millimeter mesh size here, and you'll see that SolidWorks has pulled through some default values for the others as well. I'm going to leave those at defaults, and you'll see that when I hit OK, SolidWorks is just going to very quickly whir through the geometry and break that model down into the set of finite elements that is needed to solve this static study. So there you'll see how quickly that process runs. It's very simple, and you'll see if any of you have experience using more advanced FEA tools, you'll see how simple the meshing process is here, and that's really nice, and that really takes away the complexity of the process, making it more accessible for everyone. The idea is that every designer can run these simulations with relative ease. So having a look at the mesh now, we can see that specifying those mesh controls in these areas has made it much finer, and we can see that where we haven't specified those mesh controls, that 1 mm mesh size has been applied. The final step that we would use here is to run the analysis, but what I'm first going to do is show you how easy it is to generate another study based on the one that we've already set up, because I'm happy with the settings that I've got here, but obviously I want to run a study on all of the other models as well. So I'm just going to right click on the study down the bottom here and go to duplicate. I'm going to call this next study the 2 mm fill, and I'm going to use the 2 mm fill configuration. What you'll see there is SolidWorks is just figuring out what it wants to bring through, and if I activate that simulation, you'll see that everything that I specified in the previous study has been pulled through and reapplied to this study, and we can do that again and again. So here I can go for the 1 mm fill and just use the 1 mm fill configuration. I think I hit cancel, but you see how easy it is to generate one study after another based on the same settings, which really allows us to keep that continuity between studies. One last thing we need to do, so if I switch back to the simplified study and hit run, SolidWorks is just going to run through now, and we'll see the solver window pop up any second, and SolidWorks is going to be determining, so it's going to apply those loads that we've specified, and it's going to be determining the displacements and resulting stresses as a result of the loads that we're applying. So here first you'll see in the current task, SolidWorks is establishing that stiffness matrix that we discussed, represented by the K in that motion equation. So SolidWorks is first establishing that stiffness matrix, then it's going to determine the inverse of that matrix, apply that to our force, and then we'll get our displacements. Here we can see, while the study is solving, how many degrees of freedom, how many nodes and how many elements we've used, which is a really handy tool as you get used to using the simulation package, because you can gauge how long it's going to take to solve. Now you'll see what we've got here is a pop-up. SolidWorks has realized that perhaps we're seeing quite a bit of displacement, and hence perhaps we should be considering whether the presence of stress stiffening or softening could be an issue, and also that the direction of our force application will be varying as a result of the displacement or the deflection of the spanner. We can activate the large displacements tool, which will enable SolidWorks to just iterate through a progressive application of the force, and it will change the direction, updating it so that it remains normal to the faces that we've specified. In this case, we're just going to click No and pursue with the static linear analysis. What we may have to do if we notice that we've got high yield values, or we know that the material we've used is very prone to stress stiffening or softening, we may have to go through and use a more advanced package. So now once SolidWorks has finished solving, you can see the contour plot that we've got up on the screen here. And SolidWorks has defaulted the chart values to the maximum and minimum stresses that are present within the model. So I'm just loading up that stress plot again, and we can see so the maximum stress values present within the spanner here are coming in at about 28.385 megapascals. We can also use a number of tools for looking inside our model. So for instance, the section clipping, we can drag this plane up through our model so we can see what's going inside the geometry. We also have ISO clipping tool, which allows us to isolate certain regions of the contour stress plot. So here we can see only everything that is above this stress value that we've specified here. And this really allows us to drag through and see how that stress is propagating through our model. That's a really, really handy tool there. The other thing that we've got is the probe tool, which allows us to come in, and once that tool is loaded, we can select certain areas. So say, for instance, I'm interested in a couple of points along this region here, and we can have a look and see what the stress values are at each of those locations. We can also specify, for instance, on a selected entity, so I grab that face there, ask SolidWorks to update, and we'll get a list of all the stress values associated with that face just there that we've specified. Okay. Now, we could go through and run all of the independent studies now and gain our results. I've already been through and done that beforehand, so we're just going to have a brief look at the results. One thing that we're also concerned with is the factor of safety plot. So we can define a factor of safety plot here, which asks SolidWorks to show us what the factor of safety is using another contour plot across all of the model that we've got here. If I just switch back to our presentation now, we'll see the results that we had there. So we can see how that mass and those volume values vary with each of the models, and we can see how the maximum stress values increase or decrease with each of the changes that we make. If, say, we were only interested in factors of safety above 2, we can see here obviously that 1 millimeter fill configuration isn't suitable. We can see that the 2 millimeter fill and shell configuration is just above that 2 factor safety that we need. And so being just over, we haven't got excessive amounts of structural material in there. So perhaps that's the most suitable one. All right, so that concludes our introduction to SolidWorks Simulation. This is a tool, so static linear FEA analysis is available in SolidWorks Premium. There are a number of other simulation tools that we are likely to come back to in further webinars. The SolidWorks Simulation Premium tool allows for the nonlinear and dynamic analyses that we discussed earlier, and the SolidWorks Simulation Professional package allows us to have a look at thermal, buckling, frequency, drop test, and fatigue analyses. Okay, so thank you all for attending. I hope it's been interesting and useful for you. If anyone has any questions, please use the box that you should have in the webinar program on your screens to send us through a couple of questions, and I'll see if we can answer them now. If you didn't want to see if you're not interested in any of the questions, then please feel free to head off now. Okay, so we've got a question here from a Mark who wants to know what a megapascal is. Now, pascals, obviously everyone's familiar with the Pascal term, so that's force per unit area. A megapascal is 1,000,000 newtons per square meter. So 1 pascal is 1 newton per square meter. A megapascal is that times 10 to the power of 6. All right, Mark. If anyone else has any further questions. Okay, we've got another question from Mark here. How long is the training course for linear static analysis? Typically, we'd run that over a period of 2 days, and that's a full in-depth training in terms of using the FEA tool. And we also quite often allow, for the last period of the second day, we allow you to bring in some of your own models so we can have a look at the how we can set up FEA analysis on your geometry with yourselves. Okay, we've got another one from Mark who says, what SolidWorks product is simulation in? Everything that we've seen so far today, the static analysis tool is available in SolidWorks Premium. The other tools are SolidWorks Simulation Professional, which then goes on to the other packages that we haven't seen just yet, and then SolidWorks Simulation Premium, which is the most advanced simulation package, which has nonlinear and dynamic analyses. There is also a flow simulation package. Okay, James has asked, how soon will this be available for viewing again? We have been recording this as we speak, and it should be up on the Innova Systems website within a day or two, so you'll be able to go through. Sorry, I might talk a bit quick sometimes, so you'll be able to go back through that very, very shortly. Oh, and just so you know, James, what we'll do is we'll email you the link for the video tomorrow. Okay, Jonathan, can we do similar in Simulation Express? Simulation Express is a slightly reduced tool. It's like serves as a lightweight version of the simulation tool. You're not able to conduct analyses with more than one component. So, for instance, we wouldn't be able to use the nut, that we used in this assembly here. Simulation Express only allows us to do it on one single part. We also don't get the full analysis tools that we had here, so you don't have the option to use the section clipping, the ISO clipping, or the probe tool. You do simply get that contour plot with the maximum and minimum legend on the right hand side. All right, looks like we've dried up on the questions now, so what I will do is, if you have any further questions or you think of something else later on, hopefully you'll see on your screen the support email address for us here at Innova Systems. If you forward your questions over to that address, we'll be able to get back to you as soon as we can. I'll also draw your attention to future webinars that we've got coming up. So the next one is the 16th of February. We've got sketch block design. Then following that, we've got 30 tips in 30 minutes, which is going to be a quick bash through a number of handy tips for using SolidWorks, which will hopefully increase your work speed. All right. Thank you guys for attending. I hope it's been useful, and bye.